Hi everyone, welcome to the second day of the online mini course of Subintuitionistic logics. Yesterday we talked about the modal logics and we gave you some summary of the modal logics, and today we're going to talk about the intuitionistic logics. And I mean first a brief introduction to intuitionistic logic by considering Kripke semantics and neighborhood semantics, and then introduction to sub-intuitionistic logic with Kripke models. Of course, I'm not sure that we will have time to pay attention to this or not, but anyway, we will try to pay attention to that, or maybe tomorrow. So, a quick introduction to intuitionistic logic. And for more information about intuitionistic logics, these references are very useful. So it would be better, and if you are interested to know about intuitionistic logic more, then these references are good. And the outline of our subject today will be as follows. We start by giving a brief introduction to intuitionistic logic and reviewing the preliminary notions. Also, we will introduce Kripke semantics and neighborhood semantics for intuitionistic logics. Of course, neighborhood semantics are more important for us. We then move to show how classical logic can be interpreted in intuitionistic logic by the negative translation, and how in its turn intuitionistic logic can be interpreted by another translations due to the odel into the modal logic S4 and several other modal logics. And we will the IPC is the notation for the propositional intuitionistic logic. Today we will concentrate just on the propositional of these, and just about it. But intuitionistic logic around the century old implicit in Brouwer's intuitionistic mathematics, made explicit by Hating around 1930, based on the idea of constructive proof. I'm going to give you first non-constructive or non-intuitionistic proof. We know that this theorem, I mean, there exist rational numbers R and S such that R the power set of S is rational. For the proof of this, this proof is well known since Euclid. We know that radical 2 is rational. So now, radical to power to radical 2 is either is rational or it is not. If the first one, I mean if radical 2 to power radical 2 be rational, then we can take R as radical 2 and S as radical 2 also. Then we know that R the power of S is rational, because we had this assumption at first. But if in the second case, I mean if radical 2 to power radical 2 be irrational, then we can take R as radical to power radical 2 and also S as the radical 2. Then we know that R to the power of S will be as follows, and then we can get 2. That i.e. this is rational. So we have find R and S as required, only we cannot tell what R is. So this is a non-constructive proof, and I mean non-intuitionistic proof. It's just classical proof. And in the following, we are going to first talk about the IPC language. IPC language consists of infinitely many propositional variables, I mean P0, P1, and etc. Propositional connectives, conjunction, disjunction, implication. These connectives are independent, and for example, in classical logic, we know that implication can define by conjunction and disjunction, but in intuitionistic logic, these are independent. And also a proposal constant, the falsum, or some people say contraction and falsum. And one can, negation A is defined as A imply falsum or contraction. And also A if and only if is defined as A then B and B then A. And true is defined as negation of falsum. So this is the language of intuitionistic logic. But I'm going to first introduce to natural deduction system for IPC. We have also other systems for IPC, but a natural deduction system is important for IPC. I will extend this and I will introduce I will explain about this further. Formally and intuitively, the best way to characterize intuitionistic logic is by a natural deduction system. I hope that most of you will be familiar with the natural deduction system. In fact, natural deduction is more natural for intuitionistic logic than for classical logic. A natural deduction system has introduction rules and elimination rules for the logical connectives, conjunction, disjunction, and implication. I'm going to write all of them in the here. As I wrote here, introduction rules and elimination rules. For conjunction, disjunction, implication, or falsum. Introduction of conjunction says that from A and B conclude A and B. We write this like this: from A and B we conclude A and B. Elimination of conjunction says that from A and B conclude A and conclude B. From A and B conclude A. From A and B conclude B. As we wrote here, for elimination of implication, from A and A then B conclude B. So I'm going to write the elimination of implication: from A and A then B, we conclude B. And for the introduction of implication says that if one has a derivation of B from premises A, then from premise, when I wrote like this, it means that A is a premise. Then one may conclude A then B, simultaneously dropping assumption A. And also introduction of, introduction of or says that from A conclude to A or B, and from B conclude A or B. But elimination of or disjunction says that if one has a derivation of C from A and also derivation of C from B, I wrote here, if one has a derivation of C from premise A and a derivation of C from premise B, then one is allowed to conclude C from A or B. Okay? C from premise A or B. And also here, A and B are assumptions. But above the falsum, we don't have any introduction rule. We just have that anything can be derived from falsum. Anything can be from falsum. This is called X false. I wrote here, sacred codelibel rule. And this is a Latin word, and that means that anything can be derived from falsum. So we have the natural reduction system for IPC. But now, if one wants to get classical propositional logic that we wrote this by CPC, one adds the rule that if falsum is derivable from negation A, then one can conclude to A, simultaneously dropping the assumption negation A. This is the reductio ad absurdum rule. But we don't have this rule in intuitionistic logics. This means it says that this is just in CPC, classical logics. Not that this is not a straightforward introduction or elimination rule as the other rules, as I wrote there. I think that it would be better to give some examples and proof by these systems. For example, one moment please to find. I'm going to prove the axiom Q then R, then P then Q, then P then R. I'm going to prove this axiom by the natural reduction system for IPC. So the conclusion should be Q, then R, then P, then Q, then P, then R. Now this means that P, then Q, then P, then R should be here, and also we should have premise B, then Q, then R. I wrote it like this and write the number 1. This means that this is the premise. And again, here I should have P then R, and also P then Q should be our second premise. Then R, and we should also have premise P. Now, from these two premise, P then Q then R, sorry, one moment, and also from P assumption, we conclude Q then R, and from these two, we conclude Q. Again, from Q then R, we conclude R. But we have here three premises. So in order to drop them, we should write, I'm going to write them here. The assumption 1 will be deleted. And also here, this assumption. And also here, assumption. So this is the proof for these axioms by the natural reduction of IPC. Also, I'm going to give you another example. For example, P then negation, negation P. This axiom is also true in IPC. Why? By this proof. Negation, negation, we're going to conclude P then negation, negation P. So negation, negation P should be here. We should have P. On the other hand, we know that negation, negation P by definition is defined as P then falsum, then falsum. Okay. Now, P then falsum. Now we know that from P and P then falsum, this is 1, 2. We conclude falsum, and also from one moment, see. Now negation, negation P, and this right here. Negation, negation P. From this and this we conclude this. And okay, yes, okay. And also from this and this we conclude this. This is our proof for the P then negation, negation P in the natural reduction of IPC. So we see that this will be true in the IPC. But what about negation, negation P then P? We also have this in IPC or not? I'm going to give a proof for this, and we will see that in order to prove this in the natural reduction system, we need this. Like the V then P, P, 1. Now, from this and this, we conclude falsum. Now, by this rule, that from negation P and falsum, we conclude P. So, we have this. So, this axiom will not be, this formula will not be true in IPC. This formula just is true in the CPC. IPC cannot prove negation, negation P then P. This is very important. Okay. Let's go ahead. The natural deduction rules are strongly connected with the so-called BHK interpretation. BHK is named after Brouwer-Hating chromograph of the connectives. This interpretation gives a very clear foundation of intuitionistically acceptable principles and makes intuitionistic logic one of the very few non-classical logic in which reasoning is clear, ambiguous, and all-encompassing, but nevertheless very different from reasoning in classical logic. The BHK interpretation of intuitionistic logic is based on the notion of proof instead of truth. This is very important. While we know that in classical logic, truth based on the truth. So we have A or negation A is true in classical logic, but in the intuitionistic logic, we don't have it. Generally, we can say that Brouwer-Hating chromograph interpretation of connectives. Natural deduction closely related to BHK interpretation because interpretation by means of proofs, I mean non-formal, non-syntactical objects, mind constructive. They are just mind constructions. A proof of A and B consists of proof of A plus proof of B plus conclusion, like that we saw there. A proof of A or B consists of proof of A or of proof of P plus conclusion. A proof of A then B consists of methods that apply to any conceivable proof of A will derive proof of B. And nothing is a proof of falsum. And a proof of negation A is method that given any proof of A gives proof of falsum or contraction. And now I'm going to give some examples of invalid formulas in IPC. These negation A and B, then negation A or negation B. This is just one direction of 4 directions of De Morgan's law that is not valid in IPC. Other directions of De Morgan's law are valid in IPC. And also A or negation A. that we call this the excluded middle law. And A then B then negation A or B is not true. A then B or C, A then B or A then C is not true in IPC. And A then B then B then A or B. And also A then B then A, Peirce law, that is well known as the Peirce law. And also this direction of contraction, negation A then negation B then A is not valid is not valid in the IPC, but another direction we will see that is valid in IPC. Moment to see whether it would be better to give some examples, country example I mean for this, or maybe it would be better to give some country example in the next slides. Okay. On the other hand, many basic laws naturally remain valid. Commutativity and associativity of conjunction and disjunction, both distributive laws are valid, and also these axioms. A then C and B then C, if and only if A or B then C, these, and also this that I mentioned before, the converse form of contraposition, while we know so that the converse direction of this is not valid. And A then negation A, that we have a proof for that here. And the negation A, if and only if negation B, triple negations are not needed. And also these two double negations are very interesting, because this is less obvious that double negation shift to conjunction and implication in IPC. These two axioms is interesting. We have in these in IPC. But till now, I just introduced the natural deduction system for IPC. But we also have Hilbert axiomatization for IPC that I'm going to introduce it. IPC is the smallest set of formulas containing the axiom schemes, these axioms, and close under the rule of modus ponens. And we wrote this by MP. This means that from A and A then B, we conclude B. And we wrote that. This is modus ponens. Okay. And an axiomatization of IPC is derived from classical CPC by deleting negation A then A, or alternatively A or negation A or Peirce law. As we show there, negation P is not true in IPC, and if we add this axiom to the IPC, then we can get CPC. And this means that CPC contains IPC. In fact, here this CP is equal to IPC plus P or negation P, or IPC plus negation P then P. But now about semantics for IPC. There are several semantics for intuitionistic logic that are sound and complete. Kripke semantics for intuitionistic logic and modal logic developed in the late 1950s and early 1960s. Saul Kripke proved completeness of intuitionistic logic with respect to Kripke models in 1963. So first we're going to introduce Kripke semantics for IPC. Yesterday we introduced Kripke semantics, Kripke models for modal logics, and that's why that we introduced it, because we need it here. An intuitionistic Kripke frame is a pair F WR, where W is non-empty, and the relation R is a partial order that is reflexive transitive, and antisymmetric relation on W. We defined all of them yesterday. And for the model, an intuitionistic Kripke model is a pair FV such that F is an intuitionistic Kripke frame, I mean this, and V is an intuitionistic evaluation, that is a map V from atomic to power set W satisfying the persistence condition. This persistent condition is really very important. But what does this mean? This means that if W be in valuation of P and W has a relation with some word like V, then V also should be in the valuation of P. For example, assume that this is the one word in one model that has a relation with W and with V2, with V3. If P, this means that persistency means that if P true in valuation V, and also consider that in the intuitionistic Kripke models, we should have reflexivity, transitivity, and unsymmetric. These reflexive, transitive, and transitive. So we know that all of them has a relation with itself that I will not write more time, but you should consider this, and also has a relation because of the transitivity. For example, V has a relation with V2. Anyway, persistency says that if P drew in this, then in all words that has a relation that are accessible from V, P also should be true. This means that P also should be true here, P also should be true here, P also should be here, true here. Because this also has a relation with this, and P should be also true in all of them. Of course, for example, if in this model we have another word like V4 here, that has a relation with V5, then it does not matter that P will be true in here or not, just in the models that has a relation with V. But what is the truth of formulas? The following provide an inductive definition of MW models A. For conjunction, disjunction, and proportional letters is similar to classical logics. But what is the difference is the above implication. This says that MW, A then B is true at W if and only if for all V with W or V, if V, A be true in V, then B also is true in V. This means that it every time should consider the all words that has a relation with the W. And also W will not, falsum will not be true at W. And it is easy to show that the persistency transfers to formulas. So what I mean, it would be better to write a proof for it. This means that if in model like M, A be true in W, and W has a relation with words like V, then A should be true here. By persistency and by definition of Kripke models, we have these four propositional letters. I mean, instead of A, if we have P, then we should have this. But now I'm going to show this is for all formulas. The proof of this is by the induction, that, and I'm just going to prove for you the implication case. I mean, I'm going to show that if and then I will show that. Then see. Now, in order to show this, I need, by definition of truth for implication in Kripke models, so that for all S that V has a relation with S, if MS false B, then I should also have MS false C. So, assume that V has a relation with S and B is true in S. By the assumption, we know that also W has a relation with V has a relation with S. But by transitivity, because we know that frames for intuitionistic logic are transitive, by this and also by this, we conclude that W has a relation with S. But from the other hand, this means that for all words that has a relation, is accessible from W, if B true, then C also will be true. And by assumption, here B is true in S. So by this and by this, we conclude that so the proof of this case completed. And for conjunction and disjunction also is very easy by the induction. For example, it would be better to write about conjunction. I'm going to show that if A and B and W has a relation with B, then also V in V, A and B will be true. By this, we know that in WA is true and also in W B will be true. Then by induction hypothesis, we conclude that we also satisfy A and we also satisfy B. So from these two, we conclude that A and B will be true in V. So the persistency transfers to any formulas in intuitionistic Kripke models. But about truth of formulas, since negation A abbreviates A then falsum, we can spell out the truth definitions of formulas with negation as follows. It's easy to show that MW negation A is valid in W if and only if A will not be valid in V for all V with W are V. It would be better to also write a proof for this. We know that this equal to, by definition, A then falsum, and also by definition, let's write here. By definition of truth, this means that for all V that has accessible from W, if we satisfy A, then also we should have falsum true in B. But we know that by definition of truth, we will not have this. No, never. This is not right. So this means that for all V, W are V as we want to have this. Also, the proof of this is also easy. But now, by this, I'm going to give you some examples that I think will help us to know the meaning of this. Consider this model WV that P is throwing this. And also consider that, as I said before, W has a relation with itself, V has a relation with itself, because this is the Kripke model for IPC, and we know that they are, all of them are reflexive. I'm going to show that P or negation P is not true in this model. Why? Because we know that P is not true in W. Okay, I don't write here. And also I claim that negation P is also not true here. Why? Because by definition, by what I proved this, if negation P would like to have true here, then for all V that has a relation, P should not be true in that. But now here we can see that W has a relation with V, while in V, P is true. So we conclude that negation P is not true in W. So from these two, negation P. And also I claim that negation P then is not true in this model. Why? Because as we wrote there in the slides, negation A is true in W if and only for all V with W or V there exists U such that has a relation with V, and in it A, B, U, 2. Now here, by that, negation P is true in W. We know that W has a relation with itself. Why? In W, P is not true. So from these two, we conclude this. Okay. How longer you have time? In
40 minutes.
40 minutes? Okay, so it will be to give another example, and also I'm going to show that P then Q or R, then P then Q or P then R is not valid in IPC. By I'm going to give a counter Consider this WVS model such has a relation P, Q, PR. I claim that in this model also, if we call this M, MW does not satisfy this. Why? Because we know that here, that in W, P then Q or R is true. Why? Because in W it's obvious that this is true, and also here when P is true, also Q is true, and also when P is true, R also is true. But P then Q is not true in W, and also P then R is not true in W, because in both of these words that is accessible from W, P are true, but here R is not true, and here Q is not true. So we have this, and so from this we conclude this. Okay, let's see. Okay, it would be better to have a break for 40 minutes and come back after 40 minutes. Okay, let's go ahead. And now about soundness and completeness of IPC. And first we defined these notions. A is valid in a model M if A is satisfied in all words in the model, and A is valid in frame F if A is valid in all models on the frame. And the completeness theorem is this, that means that if A is probable in IPC, if and only if A is valid in all partial order frames, Kripke frames, I mean. And the soundness is very easy, and we just need to checking all axioms in Hilbert style system, plus the fact that modus ponens leaves validity intact. So it's really easy by semantics. But above completeness of F, I just, because of the lack of time, I'm going to give just a summary of the proof. Complex can be proved by canonical model as usual. And the set of words is the set of theorized with the disjunction property. I mean the canonical models, the set of words will be this set. And gamma is a theory if A be in gamma, if and only if gamma Prof A. Gamma has a disjunction property. I mean if gamma Prof A or B, then gamma Prof A or gamma Prof B. This condition named disjunction property. And the accessibility relation defined the inclusion. As you see, in the defining of canonical model, we need to define words, we need to define relation, and also we need to define valuation. So theorized defined as this, and the relation defined by this, and the valuation defined by this. P is the set of gamma, that P will be in gamma. Then, by this canonical model, we will be able to prove that IBC is sound and complete with respect to the class of all partial ordered frames. Now we know that IPC is sound and complete with respect to the Kripke models that are partial orders and also persistent. And now the translation. I mean, I'm going to connect the relation between IPC and between CPC and also other modal logics. First, we give the so-called negative translation of classical logics. This translation, in this translation, P translate to negation, negation P, A and B translate to translation of A and translation of P, and the translation of A or B is equal to negation, negation translation of A or translation of B. And translation of A then B is equal to translation of A then translation of B. Then it has been proved that if A probable in classical logic, if and only if AN also will be probable in IPC. This is interesting and theorem. Clearly, in the most direct sense, IPC is weaker than CPC. However, from a different point of view, the opposite is true. By the negative translation that we saw in the previous slide, CPC can be translated into IPC. The formula obtained is probable in IPC exactly when the original one is probable in CPC. Thus, one may say that IPC accepts classical reasoning in a particular form and is therefore richer than classical logic. But also there is translation of IPC into some modal logics, I mean into S4 and GRZ, and I'm going to introduce that translation here. Of course, beside of this, we also have other translation that has a relation that has translate of IPC to other modal logics, but anyway, I'm just going to mention two of these. This translation called Gödel translation. The translation box into L box the language of modal propositional logics. P translate to box P, A and B translate to translation of A and translation of B, A or B translate to translation of A or translation of B, and also translation of A or B is equal to box translation of A then translation of B. then we can show that A is probable in IPC if and only if translation of A also be probable in S4 if and only if translation of A also be probable in GRZ. But S4, we introduced S4 in the next session, last session. We know that S4 is equal to K plus T plus 4. But above GRZ is equal to K plus box A. This is called the GRZ axiom. As we saw, S4 is sound and complete with respect to the finite transitive reflexive frames, and GRZ is sound and complete with respect to the finite partial order sets. Here, S4 is when we have theorems like this, then we say that S4 is called a modal companion of IPC. Of course, S4 is the smallest and GRZ is the bigger than S4, biggest, I mean, modal companion of IPC. So we could find the relation between some modal logics and also intuitionistic logics. But until now, we just introduced the Kripke semantics for intuitionistic logics. But I'm going to also introduce the neighborhood semantics for IPC. Of course, just I will brief introduction because we don't have more time. References are these two papers written in 2015 and 2022. Neighborhood semantics for IPC. Of course, I'm going to define the two kinds of neighborhood semantics for IPC. The first one is like this. As you see in yesterday, in the neighborhood semantic, instead of R, I mean accessible relation, we just have the neighborhood function. So a neighborhood frame is the PWN. It's called a neighborhood frame of IPC if W is a non-empty set and N from W to power set W is a neighborhood function such that for each W in W, we have these four conditions. W should be in the intersection of neighborhood W, and intersection of all sets that are in neighborhood W also should be in neighborhood of W. And if X be in neighborhood of W and X be under the other set like Y, then Y also should be neighborhood W, and we call this superset condition. And if X be in neighborhood W, then the set of V such that X is neighborhood V should be in neighborhood of W. Neighborhood model defined as usual by adding valuation to it. And for everything is similar, and also for we have the conditions similar to the persistence that we had in the Kripke models. Here also we have that if W be in the valuation of P, then valuation of P also should be in the neighborhood of W. This is analogous of persistency in the Kripke semantics. But above the truth in neighborhood models, conjunction, disjunction, falsum, and P defined as usual, we just have a difference for implication. Says that A then B is true in W if and only if the set V is such set V that if V be true, that A be true in V, then B should also be in true, should be in the neighborhood of W. Of course, we can write this like complement of VA union VB should be in neighborhood of W. I mean in MW force A then B if and only if complement of VA union VAB be in neighborhood of W. And for the intuitionistic negation that is defined as this, we also obtain that negation A be true in W if and only if this should be in neighborhood of W. And this is also very easy because negation E, we know that is the A falsum. By definition here, via A union V falsum should be in neighborhood of W, and we know that this is empty. So just we need to that a complement of VE be in neighborhood of W. And the similar analogous to the persistence for any formula in Kripke models, we have it also for neighborhood models. I mean, if W satisfy A, then AM should be also in neighborhood of W. And also the proof of this is very easy and by induction. And again, due to lack of time, I will not mention it. Of course, it's very, very easy and obvious. But above the completeness, completeness of IPC with respect to neighborhood semantics is also easy. And in order to explain it, I need to say something. I need to define something. A truth-preserving correspondence between intuitionistic neighborhood models and Kripke models. A Kripke model and an intuitionistic neighborhood model with the same universe are point-wise equivalent if the same formula are true in the corresponding worlds. This is the notion of point-wise equivalent. And then we can show that for every Kripke model, there is a point-wise equivalent neighborhood model. Here, instead of relation, we will have n. Or sometimes instead of r, we can write this. And the proof is very easy by defining RW this set, and also considering neighborhood of W this set. This is very easy. Then we also can get the converse of the previous theorem. I mean, for every neighborhood model W and V, there is a pairwise equivalent Kripke model WRV. And also here the proof is that by defining this, we just need to define that W is smaller than V and only if neighborhood W be under the neighborhood of V. So for every neighborhood model, we can find the Kripke model, and also for every Kripke model, we can find neighborhood model. So now we can get the completeness of IPC with respect to the neighborhood frames, because the proof relies on completeness of IPC with respect to the intuitionistic Kripke frames and the previous to the theorems. So IPC is sound and complete with respect to this kind of neighborhood semantics. Another neighborhood semantics for IPC. Now I'm going to introduce another neighborhood semantics. In this neighborhood semantics also we just have these two conditions. There exists X in everything is similar to previous. I mean a neighborhood function and W. Just we have here that the conditions are different. There exists X in neighborhood W such that W should be in X. The word W should also be in the set X. And for all X in neighborhood W and X in the X, neighborhood X should be under the neighborhood of W. And for defining our neighborhood model, just everything is similar to previous, just in the case that for analog for persistence, here we say that if W in VAP, then for each X in neighborhood of W, X should be under the evaluation of P. And the truth for this kind of neighborhood models also defined as this. A then B is true in W if and only if for all x in neighborhood of W. If x is under AM, then x also should be under BM. And also for every neighborhood model, we can find Kripke models, and for every Kripke model, we can find neighborhood models. I mean, a correspondence between them. There is a correspondence between them. So IPC is complete with respect to this kind of neighborhood semantics also. And then now, the subject of intuitionistic logic, we finished the subject of intuitionistic logics. Now I'm going to introduce sub-intuitionist logic with Kripke semantics. The outline will be as follows. I will discuss sub-intuitionist logic with a weekend implication, and this concerns logics with Kripke frames and with neighborhood frames. But today I introduce just the Kripke frames, and tomorrow we will concentrate on the neighborhood frames. We will discuss logics and completeness results. References for these sub-intuitionist logics are these, that if you want to know more about this, you can refer to these papers and some books. Of course, I think that all of them is papers, not books. Okay. But what is the sub-intuitionistic logics? Sub-intuitionist logic were studied by Corsi in 1887, who introduced a basic system F. Restal defined a similar system Sj in 1994. The system have Kripke models in which no assumption of preservation of truth is made, and also not of reflexivity and transitivity. Recall that in the frame for intuitionistic logics, Kripke model should have the persistency condition and also should be transitive and reflexivity. But in these frames of F, we don't have reflexivity, transitivity, and also we don't have persistency of evaluations. And F cannot prove formulas like A then B then A and A then B then A and B. We know that these formulas are valid in IPC. But a much studied extension BPC of F had already been introduced by Visser in 1981. It has irreflexive Kripke models with transitivity and preservation. Okay, but Corsi didn't know about Restal, and none of them know about the Visser's work. But first, we should know about the language of sub-intuitionistic logics. The language of sub-intuitionistic logic is the same language as that of IPC. It contains the connectives, conjunction, disjunction, implication, and the propositional constant. Moreover, it contains a denominable set of propositional variables. The formulas are defined as usual. Everything is, the language of sub-intuitionistic logic is exactly the same as the language for IPC. But now Kripke frames for sub-intuitionistic logics. First, we define frame as usual. And for the defining of Kripke frames, we need words, a set of words W, also named nodes points, an accessible relation R, and omniscience root G, i.e. that is that G has a relation with all of words in the W. For example, if we have something like this model, then we also should have the omniscience word that we call it G, that has a relation with all of these words and also with itself. G is a root. But for models, we add valuation to the frames and define truths as these. Conjunction, disjunction defined as usual. But for the implication also similar to the implication for the IPC, intuitionistic logic. Okay, so frames are like this. Of course, we don't need to have reflexive transitivity here and also persistency. That this is the difference between Kripke's models for IPC and Kripke model for F. I mean, without the usual requirement for IPC of R being a partial order and V persistence. And also, it would be better to consider that the omniscient root is not strictly needed. It won't change the validity notions, but makes life easier. For such rooted frames, we have A then B is true in M if and only if valuation A is under valuation B. And this makes the soundness proof smoother. We don't need to have G, but in order to prove soundness and in order to make our works easier, then we add G here. Okay. But Subintuition logic was introduced by Corsi in 1987, as I said before, with Kripke models, as in IPC, but without persistence of truth reflexivity and transitivity. So the Hilbert style for IPC, for F is as follows: these rules and these axioms. This are called conjunction, and this also called a fortiori or weakening rule. But here one can say that, and as we can see in the rules 12, I mean a fortiori rule and conjunction rule, one can weak the intuitionistic system by replacing axioms by rules. Because we know that, for example, here A then B then A is true in IPC, but replace that axioms by the rule A fortiori rule, we could weaken the IPC. About soundness of F, in any rooted Kripke intuitionistic model, and for each W in W and each formula A, if A probable in F, then W also A also will be true in W. The proof of this also is very easy. I'm going to just check, for example, the rule 12. And maybe 6. I think that 12 is very easy, and 6 would be better to check it. We just need to show that for soundness, for soundness we should check all of these rules, that mentioned in Hilbert system of F. And now I'm going to just check the modus ponens rule. So assume that for all M and for all W in W, NW force A by assumption, and for all M and for all world in M, I need to show that for all M and for all W, B is true in W. Okay. Now assume that W is in W. By this condition, by this, we know that the omniscience world, A then B is true in omniscience world. And since we know that G has a relation with all of worlds, so we know G has a relation with W. And from this assumption, we know that A is true in W. So by this and by this, we conclude that B is true in W. So we show that for all M and for all W, B is true in W. Others also is easy, the proof of others. But we need to say some properties of F. A then B then A, for example, some improbable in F, A then B then A and A then B then B, and A then B then C then B then A then C are improbable in F. I'm going to give you some examples to show why. Consider this model. In this model, we can see that in GQ is true, in W0P is true, in W1Q is true. And also we know that we don't need to have transitivity, reflexivity. For example, we don't have reflexivity here. Just we should consider that G should also have relation with all world. Now I'm claiming that in this model, then why we have this? I claim that this formula is not valid in G. Why? Because we know that G has a relation with itself, and G has a Q. Yes, G has a relation with P. So it will be better. One moment to check. G has a relation with W0, and we know that in W0 P is true, but I claim that in W0 Q then P is not true, because as we can see here, W0 has a relation with W1, and in W1 Q is true, but in W1 P is not true. So in W0 Q then P is not true. So we conclude that here in this model, this axiom is not true. Okay. And this also I'm going to give an counterexample for P and P, then Q, then P by this model. WZ G. Here P is true, here P and Q is true. Now I'm claiming that in this model, P and P, then Q, then P is not true. Why? Because as we can see here, G has a relation with Z, with W, and in W P is true, and also in W P then Q is true, because as you can see here, P is true in W, and also for every word that has a relation with W, in every word that has a relation with W, if P be true, then Q also will be true. So we also have this, but in W, P and P then Q, then so oh, this should be sorry Q. We know that in W Q is not true. So we conclude that we prove this claim. Okay, and now as we saw, A then B then A and B is not true in F. This means that we cannot have a full deduction theorem. But what is the full deduction theorem? gamma A Prof B if and only if gamma Prof A then B. This is the full deduction theorem. This means that we will not have full deduction theorem in F because we know that A then B then A and B is not true in F, but we know that in F A and B is true. So if we had full deduction theorem, then by this we should also have this, while we don't have this. So we will not have full deduction theorem. Okay, we will opt for a weak form of the deduction theorem. Weak form of the deduction theorem is as follows: A proof B if and only if A then B be provable. This can be given the more general form like this. I mean, if A1 till AK Prof B, if then A1 and till AK will be Prof B, and converse of this. The proof is very by this easy and by with the form of deduction theorem. Okay, and also this in its turn means we cannot have A and A then B, because why? It would be better to think for 1 second. Because with the weak deduction theorem, this would give us this. We have weak deduction theorem. So if we had this, then we should also have this axioms. While we know that this axioms is not true in F. So we will not have the full modus ponens. So again, this implies full modus ponens fail for deduction form assumption. So we do have a weak form of modus ponens. But what is the weak form of modus ponens? Weak form of modus ponens is like this: A then B Prof B, just if A then B should be a theorem. Just there isn't any assumption here. Others have chosen to keep full modus ponens and lose the weak deduction theorem, but we choose this form. I mean, having weak modus ponens and also having weak deduction theorem. Doshen and Restall, Celani followed mostly with logic with full modus ponens. Albert Visser had already in 1981 a logic BPC with a probability interpolation, which is a strong subintuitionistic logics. And also Dick de Jong and Maleki in 2016, following Corsi, reconstructed Restall and gave some conservativity results. Of course, I will not focus on the conservativity results. Of course, I think this slide is not related to our subject today. Tomorrow I will explain this slide more. But completeness for F, as usual, can be proved by canonical model. To show completeness of F, we need some definition. As we had for the completeness of IPC, we need to define theory and the relation, also valuation. For the theory, we need theory to define the set of walls in canonical model. A sub-sentence delta is a theory if and only if had this condition. If A be in delta, then a conjunction of them also should be in delta. If A then B be probable in F and A be in delta, then B also should be in delta. And also F is contained in delta. For theorized gamma delta, we define relation as this. Gamma has a relation with delta if and only if for all A then B in gamma. If A be in delta, then also we should have B in delta. A stop sentence delta is prime if and only if A or B in delta, then A be in delta or B in delta. Then we call this set A this set, the empty set. And then we can show that the empty theory delta is a prime theory. The proof of this is very easy, very routine. And then finally we can define canonical model as this. Canonical model for F is as a WF delta R implication. Delta here is the omniscience word. Of F is defined by delta is the empty set theory. WF is the set of all prime theorized. The canonical evaluation is defined by gamma Prof P if and only if P is in gamma. This canonical model, this is canonical model of F. And then I need to define this notion. Gamma Prof A under F is defined as A is derivable from gamma and the theorems of F by weak modal exponents and conjunction, not a fortiori rule. It would be better to notice to this. It means that if gamma Prof if gamma Prof A does not follow that under F, gamma will not have this. For example, if gamma be F, the logic F, and then F union P can prove B, but F does not prove Q, then P. And gamma and A is valid in gamma is defined as this for all M and for all W in M. If gamma be true in W, then also A should be true in W. Then we can prove this proposition, delta is theory, if and only if delta proof A, if and only if A is in delta. From right to left is easy and obvious, and from left to right, and also left to right of this section is also easy. But for another direction, we just need to use by induction on the complexity observation. It's not hard. Then we could prove this theorem. Says that if sigma doesn't prove D, then there is a prime theory delta such that delta contains sigma and D is not in delta. And the method of proof is like this. By assumption and by definition of probability, we conclude that D is not in sigma, because if D will be in the sigma, then sigma will prove D. Enumerate all formulas with infinitely many repetitions, B0 to B1, and we define these. Delta 0 is the sigma union F, delta n plus 1 this. This is a definition is important. If delta n and bn prove D, then we cannot add the formula bn to our set. In that case, we should consider delta n plus 1 as equal to delta n. Then we take delta to be the union of all delta n, and the proof is goes like other proofs. So we could prove strong completeness for F. For any formula A, sigma proof A if and only if sigma A be true in sigma. Left to right is easy, and also we prove some section of it, this soundness. But for the other direction, we assume that sigma doesn't prove A. Then there is a prime theory, gamma contains sigma as the previous theorem, such that A is not in gamma. So we will have in the canonical model, sigma will be true in gamma, and A is not true in canonical model in gamma. That means that sigma doesn't prove A. So till now, we proved that the logic, subintuition logic F is sound and complete with respect to the Kripke models that has no relation. I mean, reflexive transitivity and also persistency evaluation. But what next? The other logic between F and IPC, I mean, the wrapping persistence or transitivity. We have many logics between F and IPC that I'm going to introduce some of them here. How long we have time? Sorry. 20 minutes. 20 minutes? Okay. And now, in order to get IPC from F, we need to add some axioms, like these axioms. We call the A and A, then B are. And we can prove that this axiom characterizes the reflexive frames and its canonical model is reflexive. And also these axioms, we call this axiom T1, and we can prove that this axiom characterizes the transitive frames and its canonical model is transitive. And T2, this axiom characterizes the transitive frames and its canonical model is also transitive. These axioms, P then A then P or P then T then P, these are equivalent, characterize the models with V persistent and its canonical model is persistent. This is important that P is here propositional letter. And then the axiom PT, B then A then B, characterize the transitive models with V persistence and its canonical model is persistent and transitive. So if we add, we conclude that if we add these axioms to F, then we will get a new axiom, new logics. For example, I mean F, for example, F plus R, we will call this FR, and also for all of them. That's and also by proving this, we can say that for example, FR is sound and complete with respect to the neighborhood, with respect to the Kripke frames that are reflexive. Here, FT1 or FT2 is sound and complete with respect to the transitive Kripke frames. And FP is sound and complete with respect to the persistence models, frames, models. And also, FPT is sound and complete with respect to the persistent and transitivity. T2 and P combine to PT because transitivity is equivalent persistence for implication. I mean, if we have a transitive frames, then if in that frame A then B we throw, I mean here, just in the implication forms, and as a relation with V, then we also will satisfy B. In transitive frames. This means that, and I am going to write the proof of this. For the proof of other cases, you can refer to the papers that I introduced in the first of today. I'm going to show that A and A then B characterize reflexive frames. First, assume that F is reflexive. I'm going to show that in that frame, A and A then B is true. This means that I should show that for all M in F, on F, this is true. So for all M and for all W, then B. But this is easy because we know that F is reflexive, so W has a relation with itself, and we assume that for this we should prove that for all V that has a relation with V, if and A then B, then B also should satisfy B. So I assume that W has a relation with V, and V satisfies A and A then B. But we know that frame is reflexive, so V has a relation with itself, and so in V A is true, and also in V A then B is true. But again, V has a relation with itself, and since A is true in V, so we conclude that B is also true in V. So we could prove it. But for the other direction, I use the contraposition. I am assuming that F is not reflexive. Then I'm going to show that in F is not true. But it would be better to write P and P then. Q. So we need to choose one evaluation and one word that in that such that in that word this axiom is not true. So I choose the, of course, before that, this means that there exists V in frame F such that has not relation with itself. So I'm choose VAP exactly this node, and I claim that in this world this formula is not true, because we know that by this P is not true in V, and also P is true, and also P then Q is true, because this is obvious, and also for this, for all W that has a relation that is accessible from V, P is not true in it, and we know that here W is not equal to V because V has not relation with itself. So this is implication will be true. But so from this we conclude that P and P then Q is true, while Q is not true in this model, because we just have for in V just P is true. So we should prove that this axiom characterizes the reflexive frames. Also for others, the proof is not hard. Of course, you can see the proofs in the papers that I introduced before. So till now, we've introduced these sub-intuitionistic logics. IPC, that is our sub-intuitionistic logics. F, that is a smallest sub-intuitionistic logics that are sound and complete with respect to the Kripke semantics without any condition. And between these logics FT, FTR, FR, PR, FP, and BPC. Of course, since ft1 and ft2 did turn out to be equivalent, we will refer to both by ft that I wrote here. And business logic BPC is in our terminology the same as FTP. FTP that I call equal to BPC. As regard theorems, of course, if you consider, I mean, the theorems of them. So till now, we've introduced all of these logics that are between F and IPC. Okay. But now about translation. The translation of F into some modal logics. As you saw in the translation, in the course's translation. In course's translation, I mean, in the translation of IPC into S4, we translate P to box P because we had persistency in the Kripke semantics for IPC. But here we don't have persistency, so we need to change our translation, and we change the relation to this. Translation of propositional letters should be exactly P. We didn't change any, we will not make any change in the definition of propositional letters. But for other cases, I mean conjunction, disjunction, and implication as before, that we defined in the previous slides. But then we can show that A is probable in F if and only if translation of A should be probable in K. And this is also still course's work. And not that by this proof we can have this. So this theorem will work for the assumption also. So, and also we proved this by weak deduction theorem. So the translation works under assumptions. So we can say that the modal companion of subintuition logic F is K. K is the modal companion of F. And also BPC translates into K4 or weak K4. That I'm not going to consider this, but I'm going to just introduce that. Yesterday we said that K4 is K plus 4. But what is the weak K4? Weak K4 is K plus P and box P, then box P. This was the box P, then box P. Yesterday we showed that for characterize the Kripke frames that are transitive, but this formula characterizes the class of weak transitive. But what is the meaning of weak transitive? This means that if X has a relation with Y and Y has a relation with Z and Y not be equal to Z, then X should have relation with Z. X, Y, Z, then should X have a relation with Z. In case that X is not equal to Z, we call this the weak transitivity. So BPC translate into K4 or weak K4. I mean, this means that K4 is the modal companion of basic logics. Some people call this basic logic, BPC or basic logic. And weak K4 is also the modal companion of BPC. This case is the smallest one, I mean, smallest modal companion of BPC. So till now, we've introduced some logics between F and IPC, and also we show that S4 is the modal companion of IPC, and GRZ is the modal companion of IPC. And also we show that K is the modal companion of F. And here we wrote that K4 is the modal companion of BPC. These are very important for the tomorrow, so I mentioned in them again. Okay, thank you very much for your attention. See you tomorrow. Thank you very much.